Okay, so welcome along, ladies and gentlemen, to your weekly SETI seminar. Today we're very fortunate to be joined by Bob Wagoner, who's come down to us from Stanford University. Bob did his Bachelor's in Mechanical Engineering at Cornell, and then followed that with a Master's and PhD from Stanford. And then he moved to Caltech for his postdoc, where he worked with Fred Doyle on the primordial abundance of elements in the universe. And then he moved back to Cornell for a short period as a professor, and then back to Stanford, where he stayed until the current day. Bob's interests lie in the strong gravitational fields in our universe, in particular around black holes and neutron stars. And he's particularly interested in the technique of diskoseismology, which uses the surrounding accretion disks around stars or black holes to investigate their properties. And he's also interested in gravitational radiation from these bodies and how it could be detected by LIGO in the future. Today he's going to talk to us about mysterious oscillations in these bodies and what we do know and what we don't know about them. So if you'll join me in welcoming Bob.
You have a pointer? It's a pointer?
Oh, it's a pointer, yeah.
I'll need it eventually.
I'll get it.
Thanks a lot. It's nice being back at SETI after many years. I followed the ideas of SETI since I was on the Cornell astronomy faculty when Carl Sagan arrived, and discussions with Frank Drake then in the early 70s. So I have a fond spot in my heart for SETI over many years. I'm going to be talking about what's called QPOs, quasi-periodic oscillations, and I'll describe how they're observed. The systems we're going to be studying are binary systems, where a compact object is accreting gas from a companion star in our galaxy. And we're going to focus on these frequencies and relations between them because that's the mystery. I'll focus on the black hole systems, where we have a fundamental mystery. We see frequencies in the ratio of 3 to 2, and they're stable. So in a way, it's like atomic physics 100 years ago. Okay? We have stable frequency ratios that we don't understand. In the white dwarf and neutron star systems, the frequencies vary with time. We understand why. They're more complicated to analyze. Okay, so this is the kind of system we're talking about. This is kind of wimpy. Anyway, there's a companion star. So the tidal gravitational field of the compact object sucks material off the companion star through the inner Lagrange point here and feeds this accretion disk. Material spirals in, spirals in, spirals in, okay? Heating up as it approaches the compact object, eventually hitting the surface or the event horizon, depending whether it's a stellar object or a black hole. Okay? And so the accretion disk heats up to temperatures of order 10 million degrees Kelvin at the inner edge, emitting X-rays and gamma rays, also from a corona surrounding this disk to some extent. The corona is still somewhat of a mystery. So essentially all the data I'm going to show you has come from the heroic effort of this satellite, which has just turned off after 16 glorious years of observation. It was in a 100-minute period around the Earth. There's the photon energies detected. All this data essentially comes from the proportional counter array, just old-fashioned proportional counters. Here they are, right? With exquisite timing accuracy. There's the area, which could be larger. Not great spatial resolution, but we don't need it. We just sit on the source and count photons. And this is the all-sky monitor, which scans the whole sky every 1.5 hours looking for transient events. And a lot of these black hole systems most of them are transient. The companion star feeds the black hole only for certain periods, okay? Then it shuts off, then it feeds it again. Okay, so as I said before, I'm going to focus on the high-frequency QPOs in accreting black hole systems because, well, basically I love strong gravity. I'd like to probe the structure of curved black holes. And we're going to, as you see, get very close to the event horizon of the black hole with these oscillations. Okay? If there's time later or in the question period, I can talk about the neutron star and white dwarf accretors, which I said are more complicated. So a basic problem in this field is that we still do not have a complete theory for the origin of these QPOs. There's various theories. The ones I'm going to be talking about, diskoseismolgy, in analogy with helioseismology, just calculates all the normal modes of oscillation of the accretion disk. A two-dimensional analog is just a rubber membrane. You hit a rubber membrane and you watch all the oscillation modes of the rubber membrane. Each frequency corresponds to a different mode of oscillation of the membrane. Same thing here. The accretion disk is oscillating, okay, and emitting a spectrum of frequencies. Okay? All perturbation can be analyzed, as you know, as a linear superposition of normal modes. But there's other theories involving waves, resonances between modes, rotating blobs of hot matter, okay, which is not very well specified and probably don't exist. So here's some properties of these black hole binary systems, okay, assembled by Ron Remillard, who is the person that's feeding us most of the useful data that I'll be talking about. Let's first look at the energy spectra. And these systems come in three types of states, okay, depending upon the ratio between the accretion disk and the corona, how much material is in the accretion disk relative to the corona. In the thermal state, you see almost a pure thermal spectrum here, okay, with a high energy tail. Okay? So it's mostly just the accretion disk. In the hard state, on the other hand, you see just a power law. That's due to Comptonization of the photons emitted by the accretion disk in the corona surrounding the accretion disk, just like the corona of the sun. Okay? And then this state is a combination, okay, of a thermal spectrum and a power law. This is the state in which we see the QPOs. Now here's the power density spectrum of luminosity fluctuations. So you Fourier analyze the fluctuations in power coming off, okay? And here you can see a feature at about, see there's 10, okay? 10, feature at about 10 hertz right there. That's a low frequency QPO, which we're not as interested in because it's not as close to the black hole. Here's the feature we're interested in. You can see one at about 200 hertz here, okay? This peak, that's the high frequency QPO that we'll be talking about. All right? Clear? There'll be a quiz later, so.
Just one quick question. Define hard.
Yeah, hard means a slope here that's fairly flat, okay, compared to this is soft, okay? So hard photons mean more high energy photons relative to low energy than at this state, okay? Yeah, sorry for the nomenclature, yeah.
Is this only the X-ray spectrum or does the gamma ray spectrum correspond to the, you see the same materials in the
You don't learn as much from the gamma rays because these guys are at only a few keV, okay? The gamma rays could come from the jet, okay, et cetera, and possibly from the corona, but it doesn't get that. The corona itself is only 100 keV, okay? So you're not going to get. There is a high energy instrument that goes up to 200 keV on this satellite, okay? But there's not many photons there, okay? So most of the stuff's coming out at a few keV. So here is the key data, okay? There are 8 black hole binaries with high frequency QPOs in our galaxy. Okay, I'll say more about them later. 4 of these have at least 2 QPOs. You'll see them here. And these are the 4, okay, with 2 QPOs. This is one source. You can see a QPO at 300. You look at it later. I mean, these QPOs go off and on, okay? They're usually off. One's on, another's on, okay? But the frequencies are stable, okay? They're flickering. So here's one date. Here's another date. 3 to 2, okay? 450 to 300 hertz, 3 to 2. Here's another source. Hello? 184, 276, 3 to 2. Hard to see, but you have to believe the observers here. Here's another date, on another date. 184, 276. 184, 276. Here's another one. 113 on one day. A few weeks later, you see 168. I'll show you more data on this guy in a minute. Okay? There's also a 67 hertz QPO here, you'll see. Here's another guy, 165. A little bit later, you see a 241. You go back a few weeks later, you'll see the 165, etc. Okay? So those are the all 3 to 2, right? The highest frequency QPOs are in a ratio 3 to 2, and they're stable. Here's guys with only one high frequency QPO. This guy, this guy, this guy, this guy. So if we get a bigger satellite, detect more photons, we might pick another QPO out of the noise here, hopefully. That's the future. Okay? There's the key data. Okay? Now, here's that source, 1915. One of the lower frequency QPOs, because this one has a lot of data on it. There's 28 detections of this guy. Here's how the QPO frequency varies versus time. Okay? It bounces around a little bit, but basically stable to a percent or so. Okay? Here's how the frequency varies with QPO width. You saw those QPOs are pretty wide in frequency space, right? Like 10% or so. So no obvious correlation there, no correlation there. This is just plotted versus the total noise, the total power in the total power spectrum over all frequencies. Nothing exciting there. I don't want to focus on that. Okay. Now, just one slide of a little bit of theory. Okay, that's it. So, and to make it easy, no general relativity on this side, although the entire calculation is done within general relativity in the Kerr metric. But this just gives you the basic ideas of the physics. So here's our compact object. It could be any one of these guys. Compact. It may or may not have a magnetosphere around it. A black hole cannot have a magnetosphere by the no-hair theorem. A black hole can only have mass and angular momentum, no magnetic moments. We neglect gravitational perturbations, which is a good in the accretion. So here's the accretion disk. Okay, we'll talk about infinitesimal displacements at some position within the accretion disk of thickness 2h at some radius r. We can analyze all the perturbations in terms of this perturbation to the specific enthalpy, essentially the pressure perturbations, which, because of the stationary and axisymmetric background of the black hole and accretion disk, we can Fourier analyze in time and in angle around the z-axis, the rotation axis. Okay? The z-axis is the rotation axis of the black hole, normal to the accretion disk plane. Okay, don't worry. Buoyancy is negligible in this case, so don't worry about it. This is the buoyancy frequency, the Brun-Fossalek frequency. So for a star, for helioseismology, you've had talks on helioseismology here? Have you had talks on astroseismology? Because Kepler's going to be doing a lot with astroseismology, I think. Anyway, so we humbly call this diskoseismology. Okay? Now for a star, this is the unperturbed star. There's no velocity, just sitting there. And here are the equations of motion for any infinitesimal displacement. And the key physics here are the radial buoyancy frequency, right? And this involves the buoyancy frequency too, okay? And pressure gradients, okay? So pressure gradients involving the buoyancy frequency as well. For the accretion disk, the unperturbed disk is just purely rotating with angular velocity omega around the z-axis, okay? Now we perturb it, and here are the analog equations here. Here's the vertical equation of motion involving buoyancy again, okay? The big difference is in these two. The radial equation involves what's called the radial epicyclic frequency, okay? I'll explain that more in a minute, okay? And this equation is just conservation of angular momentum. Don't have to worry about that too much. So the big difference here is that here you're essentially gravitationally neutral, I mean just going right around the circle. Gravity is balanced by centrifugal force, okay? And when you perturb it, the orbit oscillates with a radial epicyclic frequency. If you perturb it in the radial direction, it oscillates with this frequency, the radial epicyclic frequency. That's what precesses the orbit of Mercury, is the difference. Well, sorry, I'm getting a little ahead of myself. Okay, so that's the equations of motion. And the general relativistic ones look complicated, but they basically look sort of like those equations if you put in the proper frequencies in general relativity. Okay? So here are free particle orbital frequencies that come into these equations of motion and produce all the important relativistic effects. So we have the orbital frequency omega of free particle circular orbits at any radius r in units of gm over c squared. This is frequency squared in dimensionless units again. Now, if you perturb your circular orbit vertically, it'll oscillate with this frequency. If you perturb your circular orbit radially, it'll oscillate with this frequency. Now, these frequencies squared are plotted versus radius for three cases. We define the dimensionless black hole spin A by this ratio of angular momentum to mass squared. It must vary between those limits. Okay? And so we have it for a non-rotating black hole, spinning at half maximum and almost maximum. Okay? These three plots. Now, first, let's focus on the radial epicyclic frequency. Okay? In Newtonian theory, all these frequencies are the same. In Newtonian theory, you may or may not know that. They're all the same. Okay? And you see that far from the black hole, you're Newtonian, gravity's weak, all these frequencies are the same. When you get close to the black hole, by the way, the event horizon of the black hole is at 2 for a non-rotating black hole, and as you'll see, it goes down to 1 for a rotating black hole. So there's the horizon of the black hole. Now, this turnover of the radial epicyclic frequency differing from omega is what precesses Mercury. Okay? The first great test of general relativity. And this is the same effect that will trap our modes. So our modes, our most robust mode will be trapped by relativistic gravity, not Newtonian gravity. The turnover of this, and it turns over and goes to 0, that means what? If it goes to 0 and becomes negative, your disk is unstable to radial perturbations. So the disk no longer exists here as a disk. The material just spirals quickly into the event horizon. Okay, so that's what I mean by terminates. Okay, material piles up here, but then at this point it goes unstable and spirals into the event horizon. Okay, so as we'll see in a minute in more detail, our modes are trapped by this radial epicyclic frequency. Now, see, the mass of the disk is so small compared to the mass of the black hole, you can neglect its gravity. It's a very good approximation. Again, unlike stars. Okay? It's called the Cowling approximation. Forget most of this. I just wanted to point out, this is when you turn on magnetic field, but let's not get into that. Just focus on this line, B equals 0 line. That's kappa. This is essentially kappa squared again, the radial epicyclic frequency, just to show you, okay, where the modes are trapped. Here, non-rotating hole, 80% of max rotating hole. different definition of A here, sorry. So this is our G mode. It's trapped underneath this relativistic, you can call it a potential. Okay. We'll also have acoustic modes, which will live in here. Okay. Acoustic modes are trapped between the inner edge and this radial epicyclic frequency. Okay. Or they could be sound waves out here as well. But the G modes, okay, are in here. Okay. Okay. This just shows what happens if I turn on a magnetic field, but I don't want to get into that. So here's a summary of that. Here are the regions where these modes are trapped. First of all, this G mode I'm talking about for gravity mode, okay, is trapped in this region. This is how the trapping region in R varies with black hole spin. Okay. Well, let's start. Sorry, let's start at the bottom. Here's the inner edge of the accretion disk, right, where kappa went to 0. So the accretion disk ends at 6 for a non-rotating black hole, and the accretion disk actually extends right down to the horizon for a maximally rotating black hole. Okay? Remember the horizon was at 1 in these units, okay, for a maximally rotating black hole, and the horizon was at 2 for a non-rotating. So the horizon looks like this. I didn't plot it here on this curve. So the G modes are trapped out here, away from the inner edge of the disk, and that's good, because if you oscillate material here, due to what I call the P mode and another mode called the corrugation mode, which I don't have time to go into, okay, it's essentially just a precession of the inner disk at the lens tearing frequency, which you might have heard about in connection with gravity probe B. So these modes will leak into the black hole through the inner edge of the accretion disk, right? They're bounded on one side by the inner edge and bounded by the radial epicyclic frequency on the other. Okay, so they're leaky, right? These G modes are bounded by gravity. They're not near the inner edge. Moreover, they're in the hottest part of the disk out here, away from the inner edge. This is the hottest region of the disk, turns out. So they're the most visible modes. They're the most robust modes. That's why we focus on them. Okay? So here are the fundamental mode frequencies. By fundamental, I mean axisymmetric. I'll talk about non-axisymmetric in a minute. Just focus on the G mode here, okay? These are the P mode frequencies versus black hole spin. These are dimensionless frequencies. All these frequencies scale as 1 over the mass of the black hole. Okay? It's just dimensional analysis. Okay, so here are your dimensional, your scaling to a 10 solar mass black hole. This is the frequency you expect. Okay, so this is how the frequency of the G mode varies with spin. This will be very important later when we talk about how to measure black hole spin via diskoseismology and other techniques. Okay, so I'll talk about that later. Okay, so this is just the other modes showing how they vary with black hole spin, how their frequency varies with black hole spin. Again, the P mode depends on your inner boundary conditions at the inner edge. Okay, it's sort of messy. And there's no natural 3:2 ratio here. That's a problem. Okay, we don't see a natural 3:2 ratio in these fundamental modes, okay, between any of the fundamental modes, because that ratio depends on inner boundary condition between the P and the G mode. Okay, it depends on black hole spin. Okay, the relation between the P and the G mode. So it's a little messy. Okay, so there's a lot on this slide, which I don't want to get into complete. Let's start here, which we talked about before. Here are the QPO frequencies that I showed in that collection of power spectral densities. And there's a 3:2 bold-faced in these systems. So here are the 8 systems that I talked about. Here's the mass of the companion star. Sorry, the mass of the black hole. This is the mass of the black hole here. Okay. Now this is the black hole spin determined by 2 other methods. Okay, and let me just say quickly how those 2 other methods were essentially the following. One's called a continuum method. Many of you know how you can determine the radius of a star if you know its luminosity and temperature by the Stefan-Boltzmann law, you could get its radius, right? Stefan-Boltzmann, luminosity and temperature gives radius. So if you know the distance to this system, right, you can get its luminosity. The spectrum gives you the temperature. You can get the radius. That's essentially one method. Because notice the radius is a strong function of black hole spin, right? So I can determine the radius, inner radius, I can estimate the black hole spin. The other method uses an iron line, okay? And the iron line is formed in this region. If the hole is rapidly rotating, the iron line is close to the horizon. That means a huge gravitational redshift, overwhelming even blue shifts. So you see a huge gravitational redshift in this iron line. I didn't want to talk about the data in detail. So that's called the line and continuum methods, either gravitational redshift or continuum. All right? So
Is this the Hawking radiation that you're detecting in the continuum method? No, it's the actual disk then.
yeah.
Right, okay. And the disk is traveling.
It's the thermal radiation from the disk. You've got to model the disk very well, okay? Producing that thermal spectrum I showed you earlier on. So you got to use the thermal state of the disk to use Stefan-Boltzmann law. Okay, so here's how black holes spin. Here's some determinations of black hole spin. You don't have to memorize this, okay? It's all right. Now we go over here to, now I would call this a test of diskoseismology, because we argued that the fundamental G mode should be the most observable. So one of these frequencies should be the fundamental G mode. We don't know what the second one is yet, due to what, okay? We're still working on it. But one should be due to the fundamental G mode. So we assume that for each frequency, we assume it's the fundamental G mode, we get that spin. If on the other hand, this is the fundamental G mode, we get that spin, right? Just from that plot I showed you, frequency versus spin, right? And you can scan down these. The bottom line, I don't want to belabor the point, is that these are not inconsistent with the other methods, some of which are inconsistent between themselves, okay? But let's not get into that. Like, this is a little worrisome. The continuum method gives you this range. The line method gives you that range. We predict this if this is the G mode. Notice, if the second highest is the G mode, we're okay. If the second highest is the G mode, so that's our operating. We don't know what the highest is, though. Anybody got any ideas? They're welcome to help out, okay? Now I want to show you some simulations, the best, in my humble opinion, the best numerical simulations of accretion disks for this purpose done so far by Chris Reynolds and his group at the University of Maryland. Okay? These are a little old, but very relevant. First thing I'll show is a pure hydrodynamic simulation of an accretion disk. No magnetic fields. Okay? Phenomenological viscosity was included in the second run. Okay? But I won't be showing that in detail. Then they did a run in magnetohydrodynamics, a magnetized accretion disk. Okay? These are Newtonian hydrodynamic or MHD codes, but you can approximate, in this case, the non-rotating black hole, only dealing with non-rotating black, by a modified Newtonian gravitational potential. You can mock up Newtonian gravity to look like a non-rotating black hole in this region. Okay? And they evolved this. They just started off with a finite disk and let it go for as many orbits as they could. All right? And here's what they got. Here's the hydrodynamic result. Okay? After 5 orbits and 50 orbits of the innermost, 50 periods of the innermost stable circular orbit, right? Innermost stable circular orbit. That's the inner radius of the disk. After 50 orbits and after 5 and 50 orbits. Okay? These are density contours. And there's the event horizon of the black hole, this line here, the event horizon of the black hole, right? So you're slicing through the disk, right? As the midplane of the disk. Okay, so I'm just going to show the axisymmetric results. Okay, so what's going on here? They hit the disk at time 0. 5 orbits later, there are the perturbations. Okay, and then later, everything dies away. Okay, well, that's due to numerical viscosity, which dominates the actual viscosity here. Okay, that's why it dies away. But in the meantime, they can Fourier analyze everything here, and this is what they find. They Fourier analyze in time. They do a power spectrum at each radius of the disk. Power spectrum at each radius of the disk. Okay? So now we're going to turn that previous diagram on its side. Okay? So instead of frequency versus radius, we've got radius versus frequency. But here's our old friend, the radial epicyclic frequency, how it turns over, right? So there's the inner edge of the disk at 6, right? There's the radial epicyclic frequency turning over. And lo and behold, there is the G mode right below the peak where it's supposed to be, as I showed earlier. There's the G mode right below the peak, okay, in both of these simulations, which had different resolutions. Okay? So the G mode is observed, and that's the only mode observed in these hydrodynamic simulations. Is that clear? Can you see it's living just below the peak? It shouldn't be right at the peak because the speed of sound displaces it from the peak. Pressure reduces the frequency of G modes, whereas pressure increases the frequency of P or acoustic modes. P modes or acoustic modes are dominated by pressure, which increases the frequency, but G modes are just the opposite. Pressure effects decrease the frequency. And you can see that in more detail, or not in a minute. Now we turn on magnetic fields. Okay, same thing. After 10 orbits of the ISCO, 10 orbits of the ISCO and 100 orbits of the ISCO. Okay, as you may know, you may have had simulations, these kind of simulations shown to you before. Okay, again, contours of density. And so, unlike before, in the hydro case, the fluctuations don't go away. What we've got here is the famous magnetorotational instability. You give it a seed magnetic field, it will amplify and grow and produce turbulence. Okay? Magnetic field is unstable in this kind of flows. It grows, okay, and produces turbulence. And the magnetic pressure becomes comparable to 10% of the gas pressure, roughly. Okay? Magnetic pressure, 10% of the gas pressure. Okay? So let's do the same spectral analysis at each radius. And what do we see? Nothing. Nothing there. Where the G mode should live there. G mode should live there. This is radial velocity perturbations, and this is pressure perturbations. Okay? You can see some exotica in here. Okay? Some low frequency noise, which we always see in here in these simulations. Okay? The fundamental G mode disappears. Well, disappears is really the wrong word because the magnitude of these turbulent fluctuations is 10 to the 5th times greater than the magnitude of the G mode seen in the hydro simulations. So the G mode could be buried beneath these fluctuations. Okay? So you can't see them. They're overwhelmed by the fluctuations. However, we predict, based on some semi-rigorous calculations, that unlike ordinary situations, the G viscosity, whether due to turbulence or hydroviscosity, should cause these modes to grow. These modes should grow in the presence of viscosity. However, there weren't enough orbits here to see them grow up to the magnitude needed. So I keep pushing on Chris Reynolds and company to go for more orbits to see if these modes will appear beneath this turbulence. Okay, so that's to be seen. Here's just the dependence of the mode frequency on the speed of sound I was talking about. How much it's displaced from the maximum. Okay, and in the simulations, it obeys our predicted relation, linear dependence on mode displacement versus speed of sound. So that checks our calculation for the hydro case. Okay. I'm going to try to finish at 10 of, okay? So I want to summarize, and then I have a few minutes to talk about these other mysteries, okay, to confuse you some more. Okay, so what are the mysteries? We talked about this one. Okay, everybody's clear on this one? The main mystery. I'm going to talk about this one in a minute. For neutron stars, you also have two high-frequency QPOs. They're different in two ways. They vary with luminosity, which means accretion rate, because the faster you feed material onto these systems, the brighter they are. Okay? They love to eat material. Okay? And they're losing gravity. The material's losing energy. It's radiating energy. So the faster you feed it, the more luminous they are. So these guys, their frequency varies with luminosity. How could that be? Well, let me go back quickly. How could that be? Whoops. I knew I shouldn't have done that. How could that be? Well, what's happening is, if you feed this guy fast, the ram pressure of the gas spiraling in, okay, rho v r squared, the ram pressure pushes on the magnetosphere, okay, and makes the inner edge of the disk move in. Because here, the inner edge of the disk for these guys is determined by the magnetosphere. As the accretion rate goes down, luminosity gets less, there's less ram pressure to be balanced by magnetic pressure, so the accretion disk moves out. Okay? So that's the origin of the changing frequencies. Just the inner edge of the accretion disk pushing on the magnetosphere. Okay. In addition, though, here the ratio is not constant, but the difference between the two frequencies is roughly constant. I'll show the data in a minute. And it may be quantized, although that's not as clear anymore. In these systems, we can now measure, the system I'm going to be talking about, we can measure the spin of the neutron star. From the X-ray data, you can see coherence. You can measure the spin in two ways of the neutron stars. Now you have a third frequency, the spin. So these guys seem to be influenced by the spin, which means the spin of the neutron star must be coupled into the accretion disks, where the QPOs are, via magnetic fields, right? So you're communicating the neutron star spin to the accretion disk via magnetic fields, probably. In white dwarfs, we've got a different mystery. Again, the frequencies vary for the same reason. But now we see a really beautiful harmonic sequence, 3, 2, 1, in at least this one system. And there's another mystery, which is even messier probably. There are low-frequency QPOs that seem to be, in many systems, in this ratio to the high-frequency QPOs. They're around 6 hertz or so, 10 hertz, these low-frequency guys, which nobody understands. So here's the neutron star case quickly. So spin has been measured in two ways. So nu s is the spin here. So what I'm plotting is the splitting delta nu of the high frequency QPOs, splitting divided by the spin frequency. Okay? The splitting frequency of the QPOs divided by the spin frequency versus the spin frequency. Okay? So here's the data for some systems and a new system here, which appears to have screwed things up before. Here was the proposed quantization before. If the spin is low, the splitting likes to be up here. If the spin was high, the splitting likes to be down there. Okay? So that 2-to-1 quantization. Right? To guide the eye, this is a splitting of 300 hertz. Constant. This curve just says the splitting is 300 hertz. It's not quantized like this. And here's the new system. So you decide what the mystery is here. Okay? Is it a quantization mystery? Okay, or what? Anyway, there's some relation between the QPO splitting and the spin frequency. Here's the white dwarf system. This guy is kind of unique, though, I have to admit. VW hydride. Here's the data. We're plotting period. These are called DNOs, dwarf nova oscillations, but they're QPOs. Okay? They're the analog of QPOs. Period, not frequency in this case, so you got to take the inverse, versus time in days. Okay? So each period is increasing, as I said, as the accretion rate drops, magnetosphere moves out, period increases, right? At the boundary. Right? Orbital period increases at the boundary of the magnetosphere, because there's less pressure on the magnetosphere. So it moves out like this. Then this is different outbursts, short outbursts, normal outbursts, long outbursts, super outbursts, different colors. However, at any epoch, okay, the frequencies are in a ratio of the periods in this case. The frequencies are 1, 2, 3. So the periods are 1, 1/2, 1/3. You can check it out. 1, 1/2, 1/3, 1, 1/2, 1/3. Okay, all the time. Mystery number 3. Well, a student of mine humbly tried to explain this within this general diskoseismology. This is called Newtonian G-modes, because now we're far out from the star. You don't need relativity. All these frequencies are the same, kappa and omega. But now you could trap between the inner edge and kappa or omega. You could trap the modes. Now, these are axial modes, e to the im phi, which I haven't talked about, right? Axial modes, phi dependence, cosine theta, cosine phi, cosine 2 phi, cosine 3 phi, okay, etc. Okay? Here we have 0, 1, and 2. So here's where the mode frequency is, divided by this to make it dimensionless. Beautiful harmonic modes here. This is the trapping region, not large, right? A few percent, not large. Anyway, we just played with that. Who knows? So we can get harmonic sequences. Okay, finally, what do we need for the future? Well, all speakers say we need better observations. We need more observations. We sure do, since our XTE just turned off. There's some European initiatives for the future, hopefully, one called LOFT. Okay, we need more area, more photons. Why? Remember, these QPOs pop up very rarely. We need more photons to see what is the duty cycle. Can we see them more often? Will we see more QPOs per source if we probe deeper into the noise? What's the origin of the width of this QPO? Is it lifetime? Is it frequency jitter? Okay. What is the energy spectrum of the QPO of the modulated photons? We know it's very hard, actually. It's been Comptonized by the corona. Okay, we need more simulations, as I've indicated. Okay, they suffer now from not having a self-consistent corona surrounding the disk, which we know must exist. And finally, what I'm working on, theoretical, semi-analytical stuff, we've been analyzing the flow as an unperturbed accretion disk, axisymmetric, time-independent, smooth, plus perturbations. Perturbations in terms of modes, which are low frequency, and turbulence, high frequency. Is that valid? Okay. Or is it nonlinear? Okay. Does the MRI turbulence act like viscosity? The effect of the magnetic fields on the modes, we're starting to look into. Effects of nonlinearity, could there be soliton vortices orbiting on these accretion disks? Mode-mode coupling, resonances between modes. This doesn't look too promising anymore, actually. What are the effects of the corona on the modes? Is there leakage into the corona of the modes? And finally, what does the modulation actually look like? Do the radiative transfer, compute the X-ray emission, and see what you get out. But in summary, as I tell my students, in my humble opinion, the ratio of mysteries to number of researchers in this area is extraordinarily high compared to many fields you might think of. Thank you.
Thanks, Bob. That's fascinating. The magnetic fields will not appear around the black holes, right? So
they get accreted onto the black hole, okay, but they're not intrinsic to the black hole.
Right.
Okay,
So
and they're involved with the jets too. These magnetic fields.
okay.
So they're continually accreted from the interstellar medium through the accretion disk onto the black hole, okay, and they just pile up there against the black hole. They can't go into the black hole. Just pile up. Yeah.
Very naive question, and I guess one that may be more helpful.
I'm going to turn it on.
Or I can just talk. I don't know. Right, so the naive question is how does the accretion disk know to be perpendicular to the spin axis of the black hole?
Good question. Good question. Yeah. First of all, from stellar evolution theory, for these binary systems, okay, if you evolve them, okay, everything does get aligned, okay? The black hole sucks material off the companion star, okay? That spins it up, right? So it comes in along the orbital plane continuously, okay, from the companion star, okay? So it's natural you're spinning it up around the direction it's accreting, okay? Perpendicular to the direction it's accreting. That's how they're spun up, okay? But good question. So the angular momentum of the accretion determines the angular momentum of the accretion disk of the black hole. Sorry. Yeah.
Just a little background question. How many black holes do we have in our in our Milky Way galaxy?
We're not sure. Okay, there's guesstimates of about 1 million. Okay. But
We found 8 or something.
we found 8 with QPOs, but we know about 100 total binary black hole X-ray sources. Okay.
And the term black hole binaries, is that 2 black holes?
No, black hole binaries mean ordinary star and a black hole.
And a black hole.
We've never seen a black hole binary yet. Okay. But you're right, there are neutron star binaries, okay? Right. Good question. Yeah.
One other question. Are you able to learn anything from the work that they're doing with the sun on the seismology there with things like SDO and whatnot that's going on at Stanford?
Well, I'm interested in what they're doing. And, you know, that originally got me interested in diskoseismology, okay? So I try to follow it, but things are so different in the sun. There they've got 1 million narrow, very narrow modes that are driven and damped by turbulence in the convection zone, right? For us, it's much different, okay? But, yeah. Right.
How far away is the nearest black hole, and are we feeling any effects from it?
We're not feeling any effects. It's too far away. The closest we know about is about 1 kiloparsec away, okay? Right? Which is 1/10 the distance to the center of the galaxy. Right? But don't worry about it. You're not going to be affected by black holes. Unless a mini black hole, primordial black hole, whizzes by.
How quickly is the gas being stripped off the star into orbit around the black hole?
Oh, yeah. What's the accretion rate? Ah, yeah. Gee, you would have to ask that. Numerically. Oh, that's easy. Okay, 10 to the 6, about 10 to the minus 6 solar masses per year. Okay? That's why the accretion disk doesn't have much mass either.
Okay.
So, I
think it's on.
It's on.
I think it's on.
okay. I was just going to ask, you're not enthusiastic, or you're not, you said it looks like the mode-mode coupling and resonances are not likely. Is that because you're forcing with the disk with far more energy than the Reynolds number can essentially compensate for?
No, it's a much simpler reason than that, actually. I'm glad you brought that up because I was going to mention this, okay? Hey, what about mode-mode coupling, okay? How do we get the 3 to 2? Well, if it's weak mode-mode coupling, okay, as you may or may not know, we need 3 modes who satisfy some rules. The frequencies some of the frequencies are 0. The sum of the axial mode numbers must be 0. So we could have -3, 2, and 1 for the axial mode numbers, right? Well, and we do have axial G modes, okay, right?
Yep.
But if it's 3, 2, 1, right? If it's a 3, 2 and a 3, 2, 1, right? These frequencies are too high to agree with observation. It's got to be this one, okay? You see? It's the fundamental G mode that has the right kind of frequency to agree with the observations. These two guys, the 3 to 2, are too high frequency, okay? That's why I didn't go into more detail. They're axial G modes, okay? E to the IM5, right? but they're too high a frequency to explain the observations. And they have a very small area, too, on the disk. Okay? And they're close to the inner edge, so they'll leak. Okay?
Yeah, I was just thinking of the work that, like, Balbus had done with X-ray galaxies, and
Yeah.
the idea that the local perturbations can be really important. But that wouldn't happen. This is just a global mode analysis.
But
But the local
this
modes
global
aren't
mode
happening.
analysis includes all perturbations. Okay? Any perturbation, if it's a perturbation, can be analyzed as a sum of normal modes. Okay?
Except
Any perturbation. But what you're thinking about is
except if
soliton
there's-
vortices.
I was thinking
You've got
about- yeah.
soliton vortices, that's a nonlinear thing. Okay? Right.
Yeah, okay.
Just a quick one. In all your observations, anything, has anybody in your group really tried to take and play this back against the supermassive black hole at the center of the galaxy and see how those fit together?
Good question. Unfortunately, the supermassive black hole at the center of our galaxy is in a different state. It's accreting so weakly, there isn't an accretion disk there. It's just blobby, hot, optically thin. This is optically thick, cooler stuff, okay? There's two states to accretion I didn't mention, okay? Unfortunately, the guy at the center of our galaxy does not have an accretion disk, okay?
You're saying it's blipping now.
Yeah, it's accreting stuff very slowly and blobby, okay? But it doesn't have an optically thick accretion disk. Okay? Yeah, we know that from theory and observation, actually. But in other galaxies, there are accretion disks, and we're looking for QPOs in them at periods of hours, right, and days and minutes. And there may be one detected already, a QPO in a 10 to the 6 solar mass black hole in an external galaxy, right? So it applies to those too, okay? It's mass independent, right?
I was thinking the galaxy itself, the accretion disk.
No, sorry.
Is it, I know hypothetical because there's no way to verify, but is it possible there's higher order modes that are actually inside the event horizon that are coupling back out through?
Nope.
How do we know?
We know from the no-hair theorem that the black hole, okay, just has a mass and angular momentum and a given structure with those two numbers. And you cannot communicate, once something passes through the horizon, it's gone. All it can do is affect the mass and angular momentum of the hole once it passes through the horizon. All you do is spin up the hole and make it more massive. If you throw a refrigerator into a black hole, all you do is spin it up and make it more massive. Okay, sorry.
Okay, one last question.
Yeah, regarding that earlier question concerning the spin of the spin axis of the accretion disk and the black hole spin axis being aligned.
Yeah.
Is that done through frame dragging?
Well, if necessary, in the inner parts, frame dragging does tend to align it, okay? If you happen to, and for the extragalactic black holes, they're accreting just from the blobs in the interstellar gas, right? So that accretion can even change sign, right? So this might not apply, what I said, to the big guys, right? Because there's no companion star, right? Yeah, so you have to align that with the lens tearing effects as it comes in this way, yeah. Right, but that's, right.
Okay, if there's any further questions, I'd encourage you to come and talk to Bob after this. And Bob, we have a special Are We Alone mug for you to collect a neutron star or two in.
Hey, that's cool.
Yeah, so please join me in thanking Bob for his great talk.